Your application is slow. Users are complaining. Do you redesign the entire system, or do you simply upgrade the server? This single decision separates vertical scaling from horizontal scaling, and today, we'll break vertical scaling down completely, without confusion. Stick your butts in place. Let's start. Vertical scaling, also known as scaling up, means increasing the capacity of a single server. You do not add new servers. You do not change the architecture. You do not distribute traffic. Instead, you take the same machine and make it more powerful, more CPU, more RAM, faster storage, or higher network bandwidth. The system remains centralized, just stronger enough to maintain. In simple terms, vertical scaling improves performance by upgrading hardware resources on the same machine. The application code remains unchanged. The deployment model remains unchanged. Only the capacity of the server increases. This simplicity is exactly why vertical scaling is often the first choice. In real systems, performance problems appear long before architectural limits. Early-stage products usually face slow responses, high CPU usage, or memory pressure. Not massive distributed traffic, just simple deployments. Vertical scaling exists because it provides the fastest possible fix. Instead of weeks of redesign, you can solve the problem in hours by upgrading the machine. In next few sections, we will be talking in detail about CPU scaling, RAM scaling, and storage scaling. But first, we will see how vertical scaling works. There is no magic involved. You shut down the server, upgrade the hardware or instance type, restart it, and performance improves. No load balancer, no replication, no coordination overhead. This is pure capacity expansion. CPU scaling. When you increase CPU cores, the server can handle more parallel tasks. Your server can process more requests simultaneously. This helps when your application processes many requests simultaneously, runs background jobs, or performs computation-heavy work. What actually increases in CPU scaling? Increasing the processing capability of a single machine means increasing the number of CPU cores, clock speed in gigahertz, improving CPU architecture. The key idea is to do more work at the same time, and it's not about storage network, just pure computation capacity. The main confusion occurs between CPU and threads. CPUs has physical execution unit and can execute one instruction at a time, where threads are the logical execution path. The operating system schedules it onto cores. Usual modern CPUs have one core and can run multiple threads. The key idea is, threads help but cores decide the real limit. When CPU scaling helps, and when it does not help. Let's see. When your application has to deal with heavy computation, for example, ML mod Ls and others, JSON serialization, proper encryption or hashing like used in WhatsApp, best video processing, and other heavy API logics, when your application design is not good, it's weighting of database, disk network, and API. Scaling won't help. If your CPU is waiting, adding more CPU does nothing. Here are some points for recognizing the usage patterns. In short, CPU scaling improves performance by increasing parallel execution, not by making individual tasks magically faster. RAM scaling means increasing the memory of a single server, so more data can stay in fast access memory instead of slow disk storage. RAM does not make computation faster, it makes data access faster. When data fits in RAM, applications avoid disk reads, databases serve queries from memory, and the operating system uses page cache to speed up file access automatically. This is why RAM upgrades often feel like a massive performance improvement, even without any code changes. RAM scaling helps the most when systems are memory-bound, like databases, API backends, and caching-heavy applications. If the working data set fits in memory, latency drops from milliseconds to microseconds. But RAM scaling has limits. Once the data fits in memory, adding more RAM gives diminishing returns. It also does not improve availability. A single server failure still takes the system down. So RAM scaling is powerful, but only up to the limits of one machine. In short, extra RAM helps only until your working set fits. Storage scaling means improving how fast a server can read and write data from disk by upgrading the storage device itself. This usually means moving from hard drives to SSDs, or from SSDs to NVMe. Storage scaling does not make computation faster. It reduces how long the system waits for disk operations. Since disk access is orders of magnitude slower than RAM or CPU, even small storage upgrades can create noticeable performance improvements. Storage scaling helps the most when a system is input-output bound, especially databases, file systems, logging pipelines, and search indexes. Faster disks reduce read and write latency, increase IOPS, and shorten disk queues, which directly lowers application response time. However, storage scaling has limits. Once data fits in RAM or disk speed is no longer the bottleneck, further upgrades provide diminishing returns. And like all vertical scaling, storage upgrades do not improve availability. A single server failure still brings the system down. But in real life, most of enterprises uses AWS, Azure, and Google Cloud. In cloud environments, vertical scaling becomes much easier. You can change the instance type, add more CPU or RAM, and attach faster or larger storage with minimal effort. However, the core limitations remain the same. There is still an upper limit to how large a single instance can grow, and the system still runs on one machine. Obviously, cloud does not make vertical scaling infinite. So when to use vertical scaling for your system? The right choice. When traffic is predictable, downtime is acceptable, and the system architecture is simple. It works best for small teams, early-stage products, and internal tools where reducing complexity is more important than high availability. You should avoid vertical scaling when availability is critical, traffic spikes unpredictably, or users are distributed globally. My goal is to truly understand the concepts. In the era of AI, you don't need to know exactly what to build. You need to know how to make the right decisions, so you can give the right prompts to AI. So that's everything you need to know about vertical scaling in detail. If you want to go deeper, you'll find helpful resources linked in the description. Make sure to comment and subscribe. It really motivates me to keep creating content like this. Peace out.